Hi guys, I'm going to do a little lesson on optimization because it's very important. You're going to need it for your exam, but I'm just going to focus on the classical examples because that's what's going to be on your exam, okay? And the reason why we're doing this is sort of the whole crux of the calculus. The contemporaries believe that everything in nature evolves to optimize something, to maximize or minimize it. So for an example, you can think of a sunflower. It's designed to maximize sunlight or resources such as sunlight, so that it grows properly. Your body minimizes energy, such as the amount of energy to keep your amino acids in your DNA together. And so there's all kinds of phenomena in nature that maximize or minimize things, and we use that as a tool to understand. So if we can understand nature, then we can accomplish all kinds of things, and we do understand it to some degree, and we have accomplished great things like, I don't know, traveling by airplanes at, I don't know how fast an airplane goes, but incredible speeds, right? When you fly in a plane, or even communicating on your cell phone. You can call anywhere in the world, even though there's great distance between us, we can still communicate. We create genetically engineered food, which I'm totally against, but to have enough food to feed the planet, because let's face it, without the GMOs, there wouldn't be enough food to feed everybody in the planet, which is scary, but that's another topic. So we use these things in nature to help us understand the nature, and we can express it mathematically. Okay, so super important stuff. And the great thing is that you already know how to do it. These problems seem more difficult because, number one, they're word problems. Number two, when you read them, I know how you guys read. I'm starting to do what you guys do. You guys are training me well, but you just read quick, and then you miss a lot of important information. So you have to read these problems, and you have to understand what's going on, and you have to make a picture to kind of orient yourself as to what's going on. The great thing is that once you can find a function, because that's what we're after, a geometrical function that can represent what's happening in our problem, then the rest is easy, because we know how to find absolute or global maxes and mins, right? You take the derivative and you set it equal to 0, and you solve to find the critical numbers, and you use the critical numbers along with the interval that's given to figure out what the global max or min is. Okay, you're going to do the same thing here. The only difference is you have to find the formula for yourself. So once you find that formula, you're golden, pretty much. You're out of the woods when you also find the interval. So they're not going to give you the interval, you've got to find it, but it's pretty easy. Okay, so on page 276 of the book, oh, and by the way, I'm going to do this video probably in 2 or 3 parts, because I think I'm limited to like 15 minutes per video on YouTube technically or something. So anyhow, this starts on page 276 of your book, and the first thing I want you to notice on that page is the gray box where George Best goes through what you have to do. Read the problem, reread it if you need to. Sometimes you got to read them 2 and 3 times. For the ones you're going to do, you won't have to. They're pretty cut and dry, but just letting you know. Always sketch a diagram, orient yourself, okay? Look at what's going on, see the picture. Decide what needs to be optimized, what quantity, is it volume, is it, height, is it distance, is it whatever, okay? Once you decide what has to be optimized, you say, hey, what do I know from geometry that I can write a formula for this thing as a function? Because if you have a function, then the derivative part is easy. Okay, determine the domain, which is going to be your interval, okay, of x values. And then find the global extrema by taking the derivative, setting equal to 0, solving for those critical numbers, and then what do? You plug those critical numbers along with the endpoints back into the original function to see what the biggest or smallest number is, depending on if you want a max or min. So the first problem I'm going to do, which is very, very common, is the open-topped box. It's example 1, and I'm just going to read it. I'm not going to push the book around here. and then I'm going to show you what I do. So it says an open top box with a rectangular base is to be constructed from a rectangular piece of cardboard 16 inches wide by 21 inches long. So here's my cardboard. Let me move this a little bit here. Here's my rectangular cardboard, okay? It's 16 inches, oops, you can see that, 16 inches wide by 21 inches in length. And I'm trying to get my camera up here so we can see the whole piece here, because I'm going to try to do a little demonstration, okay? The idea is we want to cut squares of equal length out of the corners of this thing, okay? So that way we can fold up the sides and create a box, okay? And what we want to do is we want to find the size of a corner that will produce an open top box with the largest possible volume. So, okay, I have this piece of cardboard. I'm supposed to cut congruent squares out of each corner of this thing to maximize volume. So I know what I'm trying to find. I'm trying to find the volume, okay? Now look, we gotta find our domain or our interval. I could take this cardboard and say, you know what, I'm gonna cut congruent squares of size 0. In other words, I'm not gonna cut anything out of there. Well, then I can't make a box, right? So my domain here is going to start at 0, meaning I make no cuts in the cardboard. Also, I'm going to use this side here since it's an even number 16. I could cut squares 8 inches, right? This is 8 and this is 8 makes 16, right? And I don't know, this is 8 and this is 8. Well, if I cut squares of size 8 out, what's going to happen? This is going to go away, this is going to go away, and then those two are going to go away. So I'm not going to have anything to make a box with. So what you do for the right end point is you find the convenient side. I could have done it with this side. You find a convenient side, 16, because half of 16 is 2. And, half of 16 is 8. And, you know, you say, hey, what if I cut squares 8 by 8? Then I'm going to have nothing left. So the maximum square I could cut and still have 0 volume is 8. So my domain here is going to go from 0 to 8. So great. I know I need a volume and I need a domain. But what I do know is if I'm going to have 0 volume if I don't cut anything, or I'm going to have 0 volume if I cut great big 8-inch squares out of this thing, then I know that my maximum volume has to be somewhere in between. It's got to be. So while these are not going to look congruent, probably pretend that they are. So here I'm cutting my squares out. Congruent squares. This is an envelope, so that's going to be a little bit weird, but I'm cutting these congruent squares out of my cardboard, and I'm going to fold up the sides, and I'm going to try to build a box of the biggest, that'll hold the most, right? The maximum volume. Okay? My little box. Okay? So, if this square was x by x that I'm cutting out here, x by x, this is x and this is x because they're congruent, then the height of my box is going to be x, right? And by the way, if I just cut two sides out of this and this was 16, this length becomes 16 minus 2x, right? And if this side was 21 and I cut two congruent squares out of this side, this is going to become 21 minus 2x. So if I know that the volume of a box is a length times width times height, then my length is 16 minus 2x, my width is 21 minus 2x, and my height is x. Voila! Not only do I have a domain from 0 to 8, but I have a formula. And once I have the formula, I know how to take the derivative of that. So let's do that. I'm going to close this book. So again, I draw a picture. I know what I'm looking for, maximum volume. And I know that I can cut nothing out of the box, or I can cut squares so big that the whole box is gone, right? So I don't want that. I want to take these little pieces out. Okay, so again, if I cut those pieces of length or length and width x by x out of each corner, then this is going to give me 16 minus x, and this is going to give me 21 minus 2x there, minus 2x here. Okay, so the formula of a volume is length times width times height. So all I do is I plug length times width times height in, clean it up algebraically. Okay, not too bad here. I've simplified it up to this point, and I decided to pull out a 2. Okay, and by pulling out that 2, now I have simplified version here, and you could leave the 2 in there, it doesn't matter. Okay, it's a constant multiple, so it's going to be there regardless. At this point here, I'm going to take my derivative. Now that this is simplified, now I'm going to take the derivative, because that's what I want to find. Okay, and then I want to set that derivative equal to 0. So remember, this is a constant multiple. It's 2 times all of those terms, so it doesn't go away. So you just leave it there. Or don't pull it out at all if you want, and pull it out later or something. But anyway, it's just a power rule here, right? So I'm taking the derivative of each term, and this is what I get. I set it equal to 0. And now I have to solve. And what I notice is, again in here, it's all divisible by 2, so I took another 2 out to make that 4. And simplified that, and then I rewrote it in descending order, because I know that's how you guys like to factor, but you don't have to factor that way. And then this factors quite nicely into 3x minus 28 and x minus 3. So when we solve for each one of these factors, we get x is 28 thirds and x is 3. Now remember that our interval is 0 to 8. So the only one here that's going to fall within our interval is this one here. Okay, so this is our only critical number. Now we know if we go plugging 0 or 8 into the original volume formula, we're going to get a 0, right? So all I really have to do is evaluate what is v of 3. So this is the critical number, so that means that this is the size square I need to cut out of each corner, because that was the question. What size square do we need to cut out of each corner in order to maximize the volume of the box? Well, if I evaluate the volume at 3, and I just did that in my calculator, I get 450. So therefore a 3-inch square should be cut from each corner to maximize the volume. You can't see that. Let me bring this up. The volume of the box. Okay. Now on your semester exam, you get to use a calculator for everything. So you know, once you have the formula, you could plug the function right in there. You notice I put my 2 outside. You don't have to. Again, it's up to you. The problem is this is going to yield huge numbers. So you know, if you're on a Zoom 4, let's say, I mean, your graph's going to look, you're going to be like, oh my gosh, I don't know, you know, I don't see anything there. There's something wrong. No, the thing that's wrong is your window. So remember that by doing this by hand, by taking the derivative by hand real quick, I know that I'm going to have this huge y value, 450. So if that's the case, all you have to do is fix your window. So the y max, I'm going to put it, say, let's do 455. Okay, and if I hit the graph key now I can see that, right? And all I have to do is second calc maximum. Okay, a little to the left of the bump, right? A little to the right of the bump. And voila, what I get down here is x is 2.9999. That's a 3. Okay, so anyway, it's just like finding the maximum on a graph. Okay, so you can do it with your calculator too. Okay, so I'm going to end this example, and I'll do a video on the next example.